Welcome students. Let us see in this video how do we implement a two input NOR gate. So I have written the Boolean expression of the NOR gate where it's given by y bar is equal to a plus b, or you can write y is equal to a plus b whole bar. This is the realization of the NOR gate using the CMOS logic. The pull down is realized using the two NMOS transistor. The pull up network is realized using two PMOS transistors. So we are trying to write the complete layout of implementation of this two input NOR gate. So over here, now I have written a NVEL, and in that NVEL I have a P substrate, and this is the background is P substrate, and I have a N diffusion being made. So this is N diffusion, this is P diffusion, and this is NVEL. So let us draw the gates. So gate is realized using the polysilicon. So this is the polysilicon what I have. So I can consider this as one of the input, which may be A, and I can have another polysilicon which is for realizing the B input. So this is B now. So we have realized two transistors NMOS and two PMOS transistors. So now we can see we have the source. Okay, let us try to identify which is the source and drain. So this is source, drain, this is source, drain, and this is what for PMOS transistor, this is source and drain, this is again source and drain. So let us write Euler's path. So Euler's path, so this is Euler's path is required to draw the layout. So let me just draw it this way. So maybe I can draw it this way. Now this is my Euler's path. So now you can draw it this way, and similarly I can draw the Euler's path for this as maybe something like this. So I can draw the Euler's path this. So this is my Euler's path. So now I have this is as per Euler's path. So it is passing through A input and B input. So Euler's path is covering A and B input in my pull down network, and it is covering same A and B input pattern in the pull up network. So that's why this is A and B. Now I can realize, or I can identify which is source drain of NMOS transistor and PMOS transistor as per the Euler's path. So this happens to be the source, and this is drain, and this is drain, this is source. And if you take this now, so this is a source, a drain, and this is source and drain. So this is what is the source drain of your NMOS transistor and PMOS transistors. Now I need to connect the metals. So let me, as you can see here, the source of A transistor of your pull-up network is connected to VDD. So let me have this as the VDD. So let me have this. Okay, so this is how the VDD goes the way down here. So this is, there is a contact cut made here so that you can connect that. This is VDD. So you can see this is connected to so and so, and I can write the VSS. So out of which, since this is source and source, these two sources are grounded. So let me have one here, and then one is over here. It goes all the way. We are trying to have all the masks that are required to realize. So this is one contact cut, this is another contact cut for connecting the two sources of A and B of the pull down transistor. This is actually VSS or the ground. So this is ground, and this drain and drain is this, and this is that drain. So I have to have a connection for this drain all the way down like this. This is now done. So this is going up this way. Okay, this is again one contact cut, this is another contact cut, and this is my Y output. So this is my complete structure. This is my complete structure. So these are various masks are put in completely here. So how do we write uh, how do we realize this using different mask? Suppose now I'll show you how do we realize this on Microwind. So Microwind is a open source tool where you can realize simple VLSI circuits. So now I have this layout to be realized. So I have to realize a 2-input NOR gate. So let me just put this aside, and then let me take this here, and then let me draw one-to-one the circuit what I have now, what is required. So now let me start with, so let me take the palette. Okay, let me just have it here. Where is this? Okay, let me just put this. Okay, this is my palette. Okay, this my palette is here. Let me put it here. Let me have the reference. Okay, this is my reference. So I will take one by one. I'll take NVEL. I'll put it here. This is my NVEL, and I'll take this N diffusion. So this is N diffusion. I will draw N diffusion here. I will draw a P diffusion. You can see this is my P diffusion. This is P diffusion. That's what I have drawn here. So this is N diffusion. This is P diffusion. Let me take polysilicon. Let me have polysilicon here, and this is input A, and this is input B. Maybe what I can do is I can slightly move this to this side. Okay, this is fine. How about this? Let me just move it over here. I'm just putting it here. Okay, now this is okay. I'm not too much worried about the dimensions. So this is A, this is B. Let me have metal here. Let me slightly minimize this. So let me just have it. Okay, what I'll do is, okay, this is, let me slightly put it here. I'll take metal 1, I'll put it all over here. So this is metal for VDD, this is metal for the ground. So I will have a metal VDD connected to this portion. So let me have this now. Okay, let me undo that. So something bad has happened. So sorry. What do I do? Let me just undo this. Where is undo? I can do that. I can do undo. Okay, fine. I have to make a contact from this to this. So I should have one more metal. And let me connect this to this. And let me connect this to this and this to this. So this is what the connections what I have here in my layout. Also can you see here? So this is one ground, this is the ground, this is VDD, and I need to connect this to this. So let me do that also. This I can do this and then do this one. Okay, now I need to make the contact cuts. For that you can just go here and then say connect layers. This is actually making the connection between the metal 1 and P diffusion, and this is for metal 1 and N diffusion. And I'll again connect this metal and N diffusion for two sources. This is drain connection, this is my output point. Connect layers, and this is my I'm connecting this. Let me have VDD to this. So this is VDD. I'll be connecting VDD here. So another VDL connected to my NVL. So this is again NVL, and this is ground. I'll connect this to ground. So let me apply input here. So this is my input. Let me make it as A. This is A input. Oh, sorry. This is A input. Oh, why this is coming like D even though if I press. Just give me a minute. So let me close a particular. I think there is an app running at the background. Let me create that. I think it is. This is that. Okay. Let me just now it will come. So now let me have this input here. This is, I just close this. It is now A. Fine. This is assigned. So this is another input. This is, sorry, I have to have another input which is B now. So this is, I'll connect it as, I'll make it as B. This is assigned. So I have to see the output here. So this is my output viewing thing. Okay, I've just made this. Let me say this is Y. This is Y. So what should happen is, as per the truth table, so as per the truth table, what should happen is, so we know that for a NOR gate, so it is A, B and Y, we are looking at 0 0 0 1 1 0 1 1. For NOR gate, if any one of the input is 1, output is 0, so it is 0 0 0 1. So if you have a combination of inputs something like this, so now this is what you have. If it is, this is like 0 0, this is let me say this as B, this as A, 0 0 1 0 0 1 1 1. So my output should be output. So this should be 1 and then 0 0 0. So this is what is expected if it is 0 0. This is now 1 and then 0. This is what we are looking at. So let me just go back to my layout and then run it now. Let me run. Exactly, this is what you have. So when it is 0 0, you have output as 1. When one of the input is 1, output is 0. You can see this is 1. This is also, of course, once this is 1, the output is 0. Here both are 1. Maybe you can just run it for some more time, maybe 20 nanoseconds. You can just reset it and run. You can see now this when both the inputs are 1 1. So of course when both the inputs are 0, then only output is 1, otherwise the output is 0. This is how you can realize a two input NAND gate, sorry, two input NOR gate. Now most importantly, we are looking at what are the masks that are required to realize this. So because now this has to be realized on the wafer. For realizing this on the wafer, okay, here I have written it on a separate sheet, where okay, we will be providing you something like this blank sheet, something like this, where you have a uniform dimensions of this rectangular mask structure. So now because if you can see, we have to have so many masks. One is for NVEL, one is for P diffusion, other is for N diffusion, and one more is for oxide and polysilicon, and it is for metal contact cut, all this stuff. So I have actually written okay, maybe let me just do one by one. So let me just I'm just blocking the things and then showing it for you. So maybe ultimately you can just have a look at okay how it comes out. This is what I have. This is my this is the overall mask what I have. This is the overall mask. So first thing is that we have to have some alignment marks. You can see this is alignment mark which is there common for all the masks. So this is the mask which is defining where does our NVEL should come. So this is where your NVEL should come. So this is, if this is your entire substrate, over here in this region NVEL come. So after getting the NVEL, so I have to have P diffusion. You can see, okay, now we are defining, of course, this is for the gate oxide and poly. You can see, of course, for gate oxide, what you can do is you can do one more what mask, where you're defining the gate oxide only in this region. Only here you have your gate oxide. Maybe I can just write where does the gate oxide mask will come. Suppose if I'm writing it for the gate oxide mask, so I have to have a alignment mark which is identical at the same point for all the masks, something like this. So these are 4 alignment masks you should be writing commonly for all the masks. So I have written 2, you can write 2 more. And where does your gate structure is coming? So gate oxide is coming over here. This is where you should retain the gate or the gate oxide. This is again gate oxide, and here you have the gate oxide, and here you have the gate oxide. This is where you're going to have the gate oxide. Next, okay, now this is where maybe what we can do is we can have the gate oxide mask. So this is gate oxide mask. This is gate oxide mask, which will define where do you retain the thin oxide in the structure. So this is my gate oxide, and this is my poly mask, that is the gate structure. This is gate oxide, that is the thin oxide, and this is my polysilicon gate structure, which is realizing these two. And then I have my P diffusion. So the P diffusion mask, if you can see, this is again the alignment masks are identical. Of course, since it is, we are writing it on a freehand, so they are not exactly placed at same point, and but in real time they all have to be at same point. That's why common alignment marks for all masks. Not, of course, this is not to the scale. It should be perfectly to the scale when you are actually realizing it. So you have your N-well and then poly mask. So this is the third mask or the fourth mask after your gate oxide. This is where you're defining this P diffusion. That's what is P diffusion. And then you're defining N diffusion. So N diffusion is defined. Then you can see we have contact cuts. So we have this contact cut. It is for this, and this. There are 5 contact cuts. Then can you see this is your metal one, where you just put all the metals. So that's what is metal one. That's what we have put here. Because when we actually realize this metal, so okay, if I can just show you that metal. So this is where your metal is. So this. So all these metal deposition will happen once using this mask. Using this mask, we're going to realize the metal deposition. And once you are done with the metal deposition, okay, that is the end of your entire structure. So to realize this NOR gate, which results in this overall layout, which is comprising of all masks, we are writing separate masks for creating N-well, polysilicon, and of course the gate structure. I have shown, okay, how does the thin oxide should be visible. So this is my thin oxide mask, and then we're going to have N diffusion mask, sorry, P diffusion mask, and then the N diffusion mask, and then we have the contact cuts for connecting the metal to the diffusion points, and then we have the final metal deposition so that you can take out the output. So the input is given at these points. But of course, if you want to have metal connection for this gate oxide also, you can have contact cut for this, but we are not indicated here. If you can see here, we are not indicated a metal connection to this gate. So that's why I'm not mentioning any metal connection for that gate structure. If you can see here, so for this gate I'm not mentioning any metal connection. So this metal connection is only for the source of your one PMOS structure and 2 sources of 2 NMOS structure, and this is for connecting the drain and drain of one drain of your PMOS structure and 2 drains of NMOSFET. So that's what is this, and this is your output point. So like this you can able to Interestingly, what we are trying to show here is the common alignment mask for all the masks, and while writing this mask, of course this has to be to the scale, so they should be perfectly aligning with each other, so that you can end up with the realization of this two input NOR gate structure. Similarly, you can try out for any other logic for that matter. It need not be a boolean, sorry, an AND gate NOR gate. You can just think of, suppose you want to realize y is equal to AB plus C whole bar, you can able to realize. So what you have to do is, so I have to write, this is my AB pull down network, and this is your C, which is the pull down representation, and then this is, if you say this is A, this is B, this will be C. To realize the pull up network, the one which is there in series will come in parallel, and the one which is there in parallel will come in series. So you will have this as your, this is now A, B, C, this is VDD, this is Y, this is ground. Now you can write a Euler's path. So Euler's path can go all the way like this. So this is ABC. You can have a Euler's path exactly the way how we wrote it for this as ABC. So now you have the gate structure as ABC, polysilicon pattern as ABC, ABC. So this is how you can able to draw a layout. Once you're done with the layout, as I shown it for the NOR gate, you have to separate out different mask for NVEL, gate oxide, polysilicon, P diffusion, N diffusion, contact cuts, and metal, so that you can realize the given Boolean expression. Hope you can able to try out for few structures.